Okay, so for those of you who I have not met, my name is Anat Shahar. I'm a staff member at the Geophysical Lab. And this is the title, Experimental and Stable Isotope Perspectives on Planetary Cores, that Bill McDonough gave me before coming here. And I didn't think anything about this title. I thought it was exactly what I do. And then last Thursday, Bill White gave a talk, and he put this slide up on the board, right, or on the screen. And he said, stable isotopes fractionate only at the surface of the Earth, right? So then I went back to my title, and I thought, well, I'm talking about planetary cores and stable isotopes, yet my professor from undergrad who taught me geochemistry was standing here telling you that stable isotopes only fractionate the surface of the Earth. So my goal in this talk is to explain to you why he said this and why I still think I can talk about stable isotopes in planetary cores. So just for some definitions, just to make sure we're all on the same page. So stable isotopes, many of the isotopes you've heard about in the past week and a half are radiogenic isotopes, right? They change with time. They have decay constants. Stable isotopes have the same ratios they've had forever. They have not changed, okay? So what we basically do is we look for elements that have more than one non-radiogenic isotope because we need to ratio them, right? So we need 2 stable isotopes or 3, or tin, for instance, has 10, for which the mass difference between the isotopes is a significant fraction of the atomic mass. And all that means is that as technology gets better, we can measure heavier isotopes, right? So in red here are what we call the traditional stable isotopes, the ones that have been measured for many, many, many decades. And if I add in blue, these are what we now call the non-traditional stable isotopes, okay? So anything that's heavier, anything that's not hydrogen, carbon, nitrogen, oxygen, and sulfur, we call a non-traditional stable isotope. And these in blue are just, I did a quick lit search, the isotopes that have been measured in the past decade, stable isotopes. So when I say fractionation, I'm going to throw around the word fractionation a lot, okay? So fractionation refers to the separation of isotopes into 2 distinct or more reservoirs. So I said that all stable isotopes have certain percentages, right? Every isotope has a percentage that was dictated by star formation, and it has stayed the same, okay? The only thing that can change that are I'm talking stable isotopes, right? Are chemical and physical processes. And when we say fractionation, we're just saying they're going into different places, into different reservoirs. And isotopic fractionations occur in 2 distinct regimes. One is in equilibrium, and one is kinetic. Kinetics refers to diffusion, evaporation, condensation. I'm not going to be talking about that at all, okay? I'm talking only about equilibrium isotope fractionation for stable isotopes. And the reason we have an equilibrium stable isotope fractionation is because we have quantum mechanics, okay? So you saw this yesterday. Energy is quantized into discrete levels, and you have the energy as a function of the vibrational frequency. And when n equals 0, the so-called 0-point energy, we still have an energy, right? It's equal to 1/2 h times the vibrational frequency. And this vibrational frequency is a function of the mass, okay? So different isotopes have different masses. Therefore, they have different 0-point energies. Therefore, they have different vibrational frequencies, and that difference will cause an isotope fractionation at equilibrium. So Edwin Schaubel made this very exaggerated cartoon, just basically showing that the heavy isotope will have a lower vibrational frequency than the light isotope, okay? And this is at the 0-point energy. So when we put a stiffer bond on a diatomic molecule, right, we have a difference in the vibrational frequencies, the heavy isotope and the light isotope. And what happens is that the stiffer bonds will concentrate the heavy isotope. It wants to minimize its energy. So a heavy isotope will preferentially go to the stiffer bond. And stiffer bonds are associated with all sorts of different traits, including they're shorter. The higher oxidation state will have a stiffer bond. So now you're thinking higher oxidation state will preferentially take the heavier isotope. And the lower coordination number. So in 1986, this paper came out. It was a review paper, and they tabulated the 5 most common characteristics that are shared amongst the stable isotope variations that are found. Now, in 1986, the only stable isotope variations were carbon, hydrogen, oxygen, nitrogen, and sulfur, right? They were the traditional stable isotopes. And what they said is that they will all have low atomic mass. The relative mass difference between the isotopes is large. So the relative mass difference between hydrogen and deuterium is 100%, right? So that's pretty easy to measure. As you get to heavier isotopes, that difference becomes smaller and smaller. They tend to form covalent bonds. They exist in more than one oxidation state, and we can measure them. What I'm going to argue to you is that many of these are actually technology dependent, right? As we get better instruments, we can measure things better, and therefore we can move on further into the periodic table. So why did Bill White say that isotopes only fractionate at the surface of the Earth? This goes back many, many decades. So if we look at a very simple isotope exchange reaction, right? So we're moving this isotope with the little prime from this A mineral to this B mineral, okay? The equilibrium constant, remember in Liz's talk, she introduced the equilibrium constant, and she basically said it was the products over the reactants, okay? Well, the equilibrium constant is equal to the partition function. The partition function is just a sum of all the energy states that this molecule can be in, okay? And that's broken up into a translational term, a rotational term, and a vibrational term, okay? So if we then define the vibrational term, the translational term, and the rotational term, we find that the vibrational term is summed over all the different vibrational modes, and it is a function of the vibrational frequency and temperature, okay? This has the B here. These are also Boltzmann constants. The translational term is not summed, okay? It's not summed because the energy levels in rotation, as well as in translation and in rotation, are so small, they're so close together that the thermal energy of the molecule is so much bigger that you don't need to sum. You can just make it an exact equation, okay? So the translational term is a function of the volume, and it's a function of the mass. And the rotational term is a function of the moment of inertia, okay? If we take all these together, we have the total partition function. And now remember, for our equilibrium constant, we're taking the ratio of these terms, okay? So when you take the ratio of the translational portion, you end up that everything cancels except for the mass. And for the rotation, everything cancels except for the moment of inertia, okay? Yes?
Can you explain that one more time? I'm curious. You explained it and I didn't get it.
Yeah.
Right, so you're multiplying all your Q's rather than adding them together.
Yes.
So it means if any one of those is 0, there's no Q.
But why would any one of them be 0?
Well, what happens if you're not free to rotate or translate?
Okay, so what we do is we say that this is kinetic and this is quantum mechanical. So when you're in a quantum mechanical state, when you only have vibration, which is what we're going to do for the rest of stable isotopes, we ignore these two terms because we say that's only kinetic. That's the beauty in what Beagle-Eisen and Meyer did in 1947 and Urey did in 1947. They basically separated this term from this term and said that these terms, when you take the ratios, are only a function of the mass and the moment of inertia, and therefore are kinetic, classical mechanics. And we're going to ignore those on the length scales and time scales that we're looking at for the atoms of vibration, for the vibrational frequency. So we're only going to focus on the vibrational frequency, and that's what they do here. So I don't want to get too into these equations, but basically this is what Urey did in 1947. These are two classical papers that in stable isotope geochemistry, Urey 1947 and Beagle-Eisen and Meyer 1947. And what Urey said in 1947 is he introduced this alpha, this reduced partition function ratio, or reduced fractionation factor, basically. The alpha is the fractionation factor. And what you're looking at is an element, or an isotope in a molecule versus that same element on its own, okay? That's why it's XR and X. And he devised this equation, but then Beagle-Eisen and Meyer, what they did that was so brilliant is that they made the fractionation factor a function of the vibrational frequency, and they related it to temperature and to mass. So now we go back to why Bill White said that there's no stable isotope fractionation, that there's only stable isotope fractionation on the surface, right? When we're talking about planetary interiors, we're at high temperature, okay? And what we're seeing here is that the fractionation is a function of 1 over T squared. So as you get to high T, this value gets very, very small, okay? And this is why people have assumed for many, many decades, based both on, they didn't assume, right? They didn't have the technology to measure the isotope fractionation factor at very high temperature, that it was basically just negligible at anything other than the surface of the Earth, okay? And mass, okay? So the vibrational frequency is also a function of mass. And so we find that as you get to heavier mass, something heavier than sulfur, let's say, the difference between the masses or between the isotopes is so small and the mass is so heavy that you're not going to be able to measure anything. So just quickly, I just showed you this alpha. This alpha is basically what we call the fractionation factor, and it's just the extension of isotope separation. And it's the two ratios, and then you're going to see this delta value a lot, and that's just the ratio of a sample over a standard -1 times 1,000. This is what we measure in the lab. And then if you subtract two deltas, right, so two different minerals, let's say, then you get what's called a big delta, not to be confused with big deltas in mass-independent fractionation, which we can go into later if we need to. And then this is also equal to approximately 10 to the third natural log alpha, which is here. So this is the classic Beagle, Eisen, and Meyer 1947 equation, which basically shows how the fractionation in two minerals is a function of 1 over T squared and is a function of what we say this is delta M over M squared, right? So M minus M over M squared, which is the same thing as this. So we've got heavy mass, the fractionation is small, high temperature, the fractionation is small. So Edwin Schaubel, in 2004, there was a Reviews in Mineralogy and Geochemistry that came out called Non-Traditional Stable Isotopes. And this was kind of the first time that people got together and started talking about all these elements. So everything that I'm going to show you today has happened in the past decade or even less, right? It's a very new field compared to many of the things that we've seen in the past week and a half where there's many, many, many years of study. This is a very, very new field and something where anybody can really make a huge impact, right? Because it's still so new. So Edwin calculates these fractionation factors, and he wrote this great review in the Reviews in Mineralogy, where he basically suggested the following rules that govern equilibrium stable isotope fractionation. Okay, so it decreases as temperature increases. There you go. If fractionation scales with mass, we've got that here. And then the heavy isotopes of an element will tend to be concentrated in substances with stiffest bonds. This I showed you earlier when I showed you the potential energy, right? So you have high oxidation state, high covalent bonds, low coordination number, low spin electronic configurations, et cetera, et cetera. But right after he put this table, he wrote, it's important to point out that these rules are largely untested. Okay? So that's all those rules except are basically theoretical, okay? That there were no tests. There was nothing showing whether or not this was actually true. The equations were there, but there were no experiments, okay? Right, so Edwin also points out that in the non-traditional stable isotopes, one or more than one of these common characteristics are actually no longer true. So these are common characteristics for the traditional stable isotopes, but not the non-traditional stable isotopes. And what is this beautiful technological advance we've had that has allowed us to now go on into the rest of the periodic table? It's this. So this is called a multiple collector inductively coupled plasma mass spectrometer. This one is mine, so I like it a lot. What you see is a computer, Washington, D.C. over there. And you have an inlet system here, which you put your sample in. You have an electrostatic analyzer, a magnet, and then collectors. So basically, you're putting your sample into this mass spectrometer. It's separating them based on their mass over charge ratio, and we mostly have single ions, so basically just their mass. And then it's going into different cups. We measure the mass the amount, literally the amount of, let's say, iron, 56 iron versus 54 iron versus 57 iron, we take the ratio, and that's our isotope ratio for that one sample. And then we compare that to a standard, because everything needs to be compared to a standard, because this instrument itself really crazily will fractionate the isotopes, right? So the idea is that you put in a standard, you put in a sample, and the instrumental mass fractionation will be the same between the standard and the sample. You can't just put in a sample and ever get anything significant out of it. Oh, yes.
Microphone.
Okay, so pardon the naivete of this question, but how do you know how much uniformity there is in these exotic isotopes in your standard?
You measure it versus an international standard that people have measured in lots of labs in which there's a known value. So there are international standards that people will pass around, and what you do so that you can compare, let's say, what I get in my lab versus what somebody else gets in their lab, right? You always have to reference it to an international standard. So the standards are different. You just need to know what they are, and they've been measured in lots of labs around the country.
So how should I think about this standard? Is it like you take a little powder of a rock, or do you take a solution, or what are you doing?
Okay, so that's a really good question. So this is particularly insightful for iron isotopes because they were brand new, and in excuse the tangent of the story. They were brand new, and then in 1999, Clark Johnson measured the iron isotope composition of lots of different things, and he basically said that igneous rocks are all the same. So he said igneous rocks should be the standard for iron isotope fractionation, right? For lab measurements of iron isotopes. And so this was 1999, so this was the first paper, right? So we have to there's a lot of credit for doing that. But the idea then would be that any standard you would need, you just pick up an igneous rock, you'd dissolve it, you'd measure it, and then you'd measure your sample versus that standard. What we now know is that actually igneous rocks are all very different, and it depends which rock you pick up. And so what I do in my lab, for example, is the standard for iron is a piece of metal that you order from a very specific company, IRMM 14, and you dissolve it, and it has a very specific isotopic composition. And that piece of metal is the same, has the same isotopic composition no matter what lab you go to. But there are problems sometimes where, as technology gets better, you realize your standards actually aren't as homogeneous as you would like them to be. NIST also has a bunch of standards that they make that they sell. But it's an important problem.
Thanks.
And I mean, the assumption that the fractionation is the same in all of these different, like the sample and the standard would fractionate the same. Is that the same as saying that the atoms don't interact when they're being deflected by the magnet? I mean, I guess, how true is that statement, I suppose?
So it's true assuming that you're putting the same thing in, okay, you have a sample and you have a standard, and before you can put them into the mass spectrometer, you have to go to the clean lab, and you need to put them through columns and make sure that the only thing you're left with is your element of interest. So I have my experiment, and I've put it through the column, and I'm left with iron in solution. And I have my standard, which is a piece of metal, and I dissolve it, and I'm left with iron in solution. If all I have is iron in solution, and it's the same solution, then the assumption that the instrument won't fractionate them differently is valid, right? The problem is that columns aren't perfect, and we have what's called matrix effects, right? And so you put it through a column, but then sometimes you miss a little bit of nickel, which is hard to separate from the iron. And that will cause a difference, because what I forgot to mention, of course, is that the reason this instrument is better at detecting some of these non-traditional stable isotopes as opposed to other mass spectrometers is because it's a plasma source. So it's at super, super high temperature. So you put your solution in, and everything ionizes. And that's based on its ionization potential, which you can't see, right? But the point is that every element has an ionization potential. And what's so great about the multi-collector ICP-MS is that it's an argon plasma, and it can ionize many, many, many of these elements, much better than the other mass spectrometers in the past were able to do. Does that answer your question?
How do you clean your instrument between experiments?
You put acid through it. So you have your solution that you put your iron into. So it's a 2% nitric solution. And when you're not running your standards or your samples, you're running the acid through the plasma. You're doing that for a couple of reasons. One reason is you don't want to change the conditions of your plasma too much. So if you're running through if you're running your standard and your sample in a 2% nitric, you want to keep your plasma in the same kind of state. So you run the 2% nitric. What you find, it's called the washout time of the instrument. And what you find is between standard and sample, for iron, for example, I'm back down at my background levels after about 2 minutes of washing it with acid. So it doesn't take very long. It has a very quick throughput. Now, mind you, that I say that it can ionize very efficiently. However, the ionization efficiency from what I put in to what actually goes into the machine is tiny, right? I think 1% or so of the iron that I actually put into the instrument actually goes through and makes it to the cups. So you need to be non-sample limited in many of these cases. Okay, so that's the machine. Now my other instrument of choice, so I have a multi-collector ICP-MS lab and I have a high pressure lab, okay? The high pressure lab is not shown here. This is a multi-anvil apparatus in Yingwei phase lab at the geophysical lab. This is the piston cylinder that I did my PhD on at UCLA. This is Craig Manning's. And then this is a diamond cell that Wendy introduced you to the other day. And so I said earlier that Edwin had pointed out that many of these fractionations that were theoretically determined were not actually, there were no experiments for them, right? And so that was about the year that I started my PhD, right? And so I was a mineral physicist, and I came into this world, and I didn't understand why there were no experiments on isotopes. And I was told over and over again, as Bill White told you last week, that it's negligible, okay? But we decided to test it out, okay? So the way we tested it is we looked at two minerals. We looked at phaolite and magnetite. Phaolite is an Fe2SiO4, okay? It's an iron silicate. It's olivine. It has iron 2+ in octahedral coordination, okay? Magnetite is a spinel. It's got iron in two different redox states, iron 2+ and iron 3+. And if you remember, I said that oxidation state is one of the ways that's been theorized to fractionate isotopes, right? So we thought, okay, can we look at the isotope fractionation between phaolite and magnetite, where here you have all iron 2+, and here you have iron 2+ and iron 3+. So if we just go through a thought experiment, we'd say, okay, if this is octahedral, and coordination number also will matter, right? So we have octahedral coordination in iron 2+, and we have iron 2+ and 3+, and octahedral and tetrahedral coordination. In both cases here, the heavy isotope will be concentrated. Therefore, if we do the experiment, we should have an enrichment in iron 57 in the magnetite. Okay? It's a very simple thought process. So this is not very difficult to do in the lab. You take a gold capsule, you put in phaolite. You have to put in hematite at first, but that's detail. Magnetite and quartz and water. Now, if you look at this reaction here, phaolite plus oxygen goes to magnetite plus quartz. And you think back to Liz's redox lecture. What is that? The QFM buffer, okay? So redox is very important, right? So we don't want the redox during our experiment to change. We don't want things moving around. So we are fixed, because we're at a constant temperature. We did the experiments at 800 degrees C. We are fixed at a temperature, so we're fixed at an FO2 buffer, okay? So the only thing that's governing this fractionation is the difference in the structure between the phaolite and the magnetite. Oh, and for those of you who don't get to look at experiments, they're actually really beautiful. These are the experiments in this capsule. So what you see here, that's magnetite, This is quartz, and these little guys are phaolite, you can see. So you can actually see the crystal habit, right, in the experiments. Okay, so here is a plot where you're looking at a big delta, which is the little delta of magnetite minus the little delta of phaolite, of iron 57, as a function of 10 to the 6th over t squared, that 1 over t squared, right, that we saw from the Beagle-Eisen and Mayer equation. So you have fractionation increasing in the y-axis, and you have temperature increasing as we get towards 0, right? Because at infinite temperature, there is no fractionation, 1 over t squared, right? And these two curves are the two theoretical calculations that had been done prior to us doing the experiments. And what we found is that the experiments line up perfectly with the theory, okay? So what have we just found? Not only did we find that magnetite and phaolite actually do behave the way they should, but we also found that at 800 degrees C, which is much hotter than the surface of the Earth, there is an isotope fractionation that we can measure. And it's actually not that small. Okay, so our precision is on the order of 0.02, 0.03 per mil. This is 0.4 per mil, right? This is well outside of the precision. So we have a fractionation at high temperature.
So at the surface where you would have larger fraction, how large is this with respect to things that people are interested in traditionally?
So hydrogen isotope fractionations can be on the order of hundreds of per mil, right? So carbon, in the Earth we have the mantle is -5 and the surface is -25. So it's much, much bigger. The non-traditional stable isotopes, the fractionations are much smaller, as you would expect, right, based on the theory, but big enough that we can measure. That's what makes it different.
In what sense is that perfectly agreement with the theory? I mean,
well, there are two theoretical calculations, and we
so
fall right in the middle.
Consistent,
yeah.
I see. So it's the experiment is the averager, I guess.
That's right. I didn't want to.
The robust part of the theory is you should form a line against 1 over t squared. The slope is.
That's right. Okay, but now we want to go back to planetary interiors. So I gave you that whole introduction to basically explain to you that there is an isotope fractionation at high temperature. But now we want to get to more than 800 degrees C, right? We're talking about planetary interiors, we're talking about cores, we're talking about mantles. And, well, I guess I just gave it away. So the idea, right, is that Mercury, Earth, and Mars have a core, and they have a mantle. And the question is there a fractionation that occurs when that core separates from that mantle? Okay, during differentiation of the planet, is there a stable isotope fractionation, and can we find it? Right. So okay, maybe there was, and it's gone now because it's been 4.5 billion years or so. But can we actually pick up a rock and say this rock still has a signature of core formation on whatever planet? So for Mars, we would use Martian meteorites, and I'll show you what we can do for Mercury, but on Earth as well, right? In order to get to this point, I wanted to just say again that, so this paper by Francis Birch in 1952, you can't see that these are highlighted slightly, noted that the density of the outer core is lower than that of iron by about 10%. Okay? So what does that mean? In a very schematic way, if you have depth and density, this is what we find with Prem, and this is the density of pure iron. Okay? So that means that there must be something lighter in the core in order to match the density that we find with seismology.
Go back one slide. I'm going to waste 15 seconds of your time to save a minute of my time. Birch 52, he didn't know whether there was a density difference because he only had static high-pressure experiments. Birch 62, it was the shockwave measurements that made it clear that there is a density deficit.
That's right. That's right. That's a good point. Okay, so now we know that there's a density deficit. We know that we need something lighter because nickel won't do this. Okay, we know there's an iron-nickel core. The nickel won't do this. But there is something else that makes the core what it is. There are light elements in the core, and we presume that this happens on all cores. So this is where we turn to mineral physics. So the mineral physics community for a long time has done lots and lots and lots of experiments where they've put in iron and some light element, right? The ones that we tend to think about are hydrogen, oxygen, sulfur, silicon, and carbon. And they will say, if I take iron to high temperature and high pressure and I add this element, will it actually go into the iron? Will this be a happy, stable mineral or phase? And what they found is that yes, so you can get hydrogen, oxygen, sulfur, silicon, and carbon into iron in all sorts of different phases. And what you see is you can do one of these. This is from the treatise in 2004. I'm sure this has changed since then, but I liked this plot. So if you look at the relative density deficit with respect to iron as a function of the mass fraction of the light element, you see that you can get this 10 weight %, right, in with lots of different light elements.
Is where those lines stop, is that, so where those lines stop, is that the limit of how much you can stuff into iron, or is that just the
This
limit of
is
the
based on experiments. And so she basically took a whole bunch of experiments and just drew lines and compiled it into one plot. You shouldn't look at this area as, it's not theoretical, right? It's an experiment.
So for example, that carbon Fe3C curve stops before you can meet the density deficit. What you're saying is that doesn't mean that that's the limit of carbon that you can dissolve in iron.
No, because
that's just where the experiment stopped.
There's another phase. Right, but there's another. That's right. What I'm not showing you is that the phase at higher pressure is Fe7C3, which would be more applicable, right, to the core pressures and which would be able to push it up higher.
Yeah.
As Mark just said, this is the exact. It's Fe3C, right? You can't change the carbon content.
Okay, and are those at core pressures and temperatures? Yeah, probably not.
I doubt it, but I don't remember what. I think they're probably multi-envol diamond cell experiments.
So they're low by an order of magnitude in pressure?
Yes. It's just to show that you can put light elements experimentally into iron, right? That's the bottom line. What?
These are all solids.
Solids.
Oh, okay.
There's several logical steps to get from here to
Right.
the other one.
Yes.
Right.
But just to say that they do like each other. Carbon will go into iron, and hydrogen will go into iron.
I also want to point out that the density deficit that initially put forth by Birch and frequently talked about by the community, and the number often heard is 10%, is somewhat misleading, and it's very dependent upon a number of parameters. And the most important, in my mind, is the temperature of the outer core. And so it's actually been a sort of a misinterpreted phenomena to refer to it as 10%.
So this is what I asked Jessica after her normal modes talk. I don't know where she is. There she is. You know, I said I keep saying 10%, but is it? I mean, it's been 10% since 1962. Is it still 10%, right? And you were saying you're working on. Yeah. But maybe normal modes can help us get to this.
I mean, Bill's point is that if you change the temperature of the
Right.
core by making it hotter, for example,
Right. That's right. That's right. That if you change the temperature of the core, then the density will change.
If you change your estimate of the temperature of the core, you're not actually changing the temperature of the core.
Very true. Thank you. If only I had the ability to do that, right? Okay, so experiments show that light elements do go into cores, but importantly, as you all just pointed out, there are lots of problems with trying to figure out just from these data what is actually in the core. Okay. Another thing to take into account is that FO2 has a huge influence on what will go into the core. So what you see here is that silicon will go into iron at very low, this is relative to iron wustite, at very low oxygen fugacities, but sulfur will go at slightly more oxidizing conditions. There are also problems such that sulfur and silicon, if you combine them, have a miscibility gap up to a certain pressure. There are all sorts of games you can play with experiments with FO2, composition, temperature, and pressure. But the bottom line is that you can get these elements into the core, but the proportions of the elements, pretty unclear. right? So it's probably not just one element that's causing the density deficit. It's probably more than one. But we're not really sure which one and how much.
So this is all solid.
This is all solid.
Any liquid?
I think they're just much harder to do. I don't know. This is liquid. This is all solid. This is all solid.
There are experiments on liquid, typically in multi-anvil pressure ranges, so it's a long extrapolation to cores. And there are some shockwave measurements that access the liquid field.
At the point of core differentiation, what do we think the FO2 at that point was?
Okay. So people will throw around numbers such as iron wustite minus 2.5. A paper by James Badrow and the IPGP group in Science came out last year. It's CIDER et al. And they found that they actually think that that the FO2 during core formation was much, much higher, close to QFM. So it ranges in what you think, because they want to put a lot of oxygen into the core, so they're trying to get a lot of oxygen around, right?
So if you go back to the next slide, then that says something, so if you want to put a lot of oxygen, then that means you can't put a lot of...
But remember, it matters also what temperature you're at, right?
Okay.
And so it's a game. We know that we have iron in the core, right? So we know we need to be at a certain FO2, right, for the iron to be there. As to exactly what it was, this is where Liz was getting to in her lecture, that we think we started maybe around here, but it's probably unclear.
And just to get a sense, how important are the relative effects of FO2, temperature, and pressure on these sort of partitionings? Are they all sort of all sort of equal, very significant, or is some more significant than others?
I don't know how to put them in order. I would say they're all very important.
So to think about the FO2 during core formation, the constraints appear to be, okay, the core is mostly iron, and the mantle has some FeO in it.
Right.
So you can't go too reducing in a simple scenario where there's no FeO left in the core. Right? So the activity of FeO in the mantle is about 0.1, right? So you're a log unit below QFM. Or you can say, we'll start out super reducing, we'll extract all the iron from the mantle, and then after core formation we'll add it. So you can make up whatever scenario you want to doctor these things. The simple models put you pretty close, a couple log units below iron wustite, but the simple models aren't necessarily right.
That's right.
Right, and sorry for my gasp.
No, it's okay.
The overall point made by Paul is that we should never think of core formation as a singular event.
Yes.
And Bill reminded us that it's quite possible at some stage, beginning, later, etc., that there could have been the accretion of pre-differentiated planetesimals with their own cores and merging of cores.
Yes.
So it's very important for us to be very understanding of, we don't understand it, and very understanding of the fact that it is very likely that core formation happened over a range of P, T, X, FO2.
That's right. And so what many people will do now is they will give an average pressure. So on average, the pressure during a multi-stage core formation was 40 gigapascals, is the number that's thrown around sometimes, right? Or the average temperature over that core formation time scale is whatever temperature, 4,000 Kelvin, 3,000 Kelvin, okay? But it was almost definitely a multi-stage process.
Probably we should let Anat continue with her lecture, but just to continue on this theme a little bit longer. First of all, to continue what was just said, the temperatures and pressures of core formation had to evolve because the planet was growing, so the early pressures could not have been as high as the later pressures. Right. Second of all, what's coming out of models of accretion at this point is that the compositions of material accreting to the Earth through time were probably evolving. And very popular models, not necessarily correct, are that more reduced, more instantite chondrite-like materials were accreted initially, and that so initial core formation was under very reducing conditions, and it evolved to more oxidizing conditions.
That's right. You could not have set me up better for what I'm about to say. Okay, silicon isotopes. Okay, so what have we learned? We've learned that isotopes will fractionate at high temperature. we've learned that core formation is a very complicated process, and that the models and the mineral physics data alone have not necessarily been able to pin it down, right? In come non-traditional stable isotopes. Can we come up with an independent measure of the light elements in the core without any of that information, okay? So a paper was published in 2007 by Bastian Georg, working with Alex Halliday at ETH at the time, I think. And what you're looking at here is delta 29 versus delta 30. We call this a 3-isotope plot. It's 3 isotopes because the denominator in both of these is 28 silicon. So we always have ratios, right? 29, 28, 30, 28. And you see that all these points lie on a line, which is called the terrestrial fractionation line, which is a theoretical, you can calculate it just based on the masses of the isotopes, okay? And why this paper got into Nature is that they found that the Condrites, okay, so the meteorites, were different in their silicon isotope composition to the moon and the Earth. Now, assumption number one, everything in the solar system was formed from the same material and should therefore have the same silicon isotope composition, okay? This is a stable isotope, so it can't really change due to processes that might have occurred in the early solar system. Okay, so that's assumption number one. So we're saying chondrite, bulk chondrite, is bulk solar system, and we're saying Earth, because we can't measure the core, is bulk silicate Earth. So we're saying bulk silicate Earth and Moon are different than bulk solar system. Why? Okay, so what they say in this paper is that it's due to core formation. Okay, so what they're saying is that you take the Earth's mantle. If you look, this is I took this from your treatise paper. I just made it. I added colors. Magnesium silicon versus aluminum silicon. You take the Earth's mantle. If you add in silicon, you end up with the silicon composition much more similar to what we would expect for the total Earth. Okay. So at this point, I was still a PhD student, and I was reading this paper, and I quickly got on an airplane and flew to the geophysical lab to do some experiments, because obviously, if they are saying that this is due to core formation, right, they have no isotope fractionation factor. They have no idea, because they couldn't, because the experiments didn't exist, what the fractionation is between metal and silicate that could cause this fractionation. Edwin Schabel, again, is on this paper because he calculated what the fractionation factor should be, but there were no experiments, okay? So we had shown experimentally that isotopes or iron fractionate at 800 degrees C, but this is much higher temperature than that, right? This is core formation. And what we're assuming, I'll show this again, everybody likes to show this same figure, is that in a core formation scenario, in a very simplified core formation scenario, this is a single stage model, but it would work also for a multi-stage model if we just assume that the iron and the silicate equilibrate, and then the iron goes down into the core. Okay, so the equilibration occurred somewhere up here, and then it just kind of fell down into the core. Now we need the equilibrium in order for all of our previous assumptions that I've been telling you about to be valid. Okay? So again, we're comparing chondrites to experiments to tell us something about core formation. Okay? This is what experiments look like when they're at very high temperature. So this is a silicate glass, and this is a metal blob. Okay? It starts off as a homogeneous mixture, hopefully, of the two. So you have very fine-grained metal and silicate, and it's all synthetic silicate, so we put in exactly what we want. We grind it all up. We put it up at high pressure and temperature. Everything melts. All of our experiments are liquid-liquid. Okay? Everything melts, and we end up with this really great-looking planet, right? It's a little planet. So you have a core and you have a mantle. And then you take your core and you take your mantle and you dissolve them in the clean lab, and then you put them through your mass spectrometer and you get a fractionation. Now, I'm making it sound like it's not that difficult, but proving that you're at isotopic equilibrium, which is key, again, is very, very difficult. And I won't get into how we do that, but you'll just have to trust me that I've spent many, many, many years trying to figure that out. And again, we can put it into the mass spectrometer. There are two different ways that we've measured the isotopes. One is, like I said, you put it through the column, and then you put a solution into the plasma. But the other is to use a laser. And the benefit of using a laser is that you get in situ isotope fractionation, in situ ratios, isotope ratios, right? So when you're doing experiments, Wendy gave you lots of things to be wary about when you're looking at experimental data. One of the things that I'm most worried about is capsule material, the interaction between what's going on inside the capsule and the material on the outside is very important, right? Because you're at very high temperature and lots of things are moving around. And so whatever you choose as your capsule material will have an effect on the composition of your experiment. But if you use your laser, you can go in and just put your spot exactly where you want it to be, and you don't necessarily run into some of these problems, okay? Or at least we thought. So here is a piece of metal that I've polished, and I don't know if you can see, this is all the silicate around it. You can't see the holes in the silicate very well, but you can see the holes in the metal, okay? So these holes, their ablation spots are 80 microns, okay?
So just for interest, going back to what you said earlier,
yeah.
Do you then have to be careful about the other elements you've then got from your ablation in your mass spectrometer?
So that's a really good question. So matrix effects in laser ablation are important because you are not just looking at iron. You're looking at iron plus all the other stuff in your silicate or your metal. And I will tell you that the answer to this question depends heavily on who you're speaking to. I think, okay, in silicon isotopes, we tested whether or not there were matrix effects by looking at, we made glasses, and we put in all sorts of different elements into the glasses. And then we looked to see if there was, but with the same isotopic composition. And then we looked to see if there was an effect based on the composition on the silicon isotope ratios that we measured. And the answer was no for silicon. We basically could have used the metal as a standard for the silicate. It was so good, right? But a lot of other people will tell you that you need a femtosecond laser or that you have lots of matrix effects. I don't actually believe that. I think you just need to be very careful as to how it's all set up. And there are lots of, gas flows. There are lots of variables that I can tell you about. Okay, so these are the data from those experiments, right? So we have metal and silicate, and we're looking at the silicon isotope ratios between the two. And we have 29 silicon again and 30 silicon. There are 3 experiments. This is a lot of data for those of you who don't do experiments. This takes like a year. So I know it only looks like 6 points, but still. Okay, so we noticed one thing, right? The silicate is up here. The silicate doesn't change. I haven't told you what the difference is with the experiments yet, but I'll tell you that the silicate doesn't change. Why does the silicate not change? Because the majority of the silicon in the system is in the silicate, right? So if I perturb the isotope ratios in the metal, my bulk value of my system is still very much set by my silicate, because at most I'm getting 8% silicon in my metal. So that's good, okay, that our silicate doesn't change its isotopic composition. The metals are at different temperatures. They show you the fractionation as a function of temperature.
Was the silicate molten?
Yes. It was a liquid-liquid experiment. This is 1800 Celsius. This is 2000 Celsius. And this is 2200 Celsius. Okay? These are very high temperatures. Okay? And what you see is that as the temperature increases, my fractionation gets smaller, right? The difference between the green and the red gets smaller as the temperature increases. But there is an isotope fractionation at 2000 degrees Celsius.
What pressures of the experiments?
What pressures? I don't remember what's plotted here. So in that paper, so she asked what pressures these experiments were done at. We haven't gotten into pressure yet. Hopefully we will. But these experiments, I think, were all done at 1 GPa, but we also did experiments at 7 GPa and found that there was no difference with the pressure. Now, that brings up a good point. Why don't you do your experiments at very high pressure, right? Because then there's not enough stuff to take out and put in the mass spectrometer. Okay, so as you get to higher pressure, your sample size gets smaller and smaller and smaller. But I still need to physically separate two phases and dissolve them in a chemistry lab and then put them into the mass spectrometer, right? So there's a limit when it comes to these sorts of experiments of how high pressure you can actually get to.
So how large of a sample volume do you actually need to measure? And so, and related to that, I mean, with things like focused ion beams and that sort of thing, if you could get out smaller samples with those, would that be enough to measure?
If I could get a sample that you told me you were sure was 100% silicate or 100% metal, and I could physically touch them with a needle, be it, right? Then yes, that would probably be enough in terms of the isotope, in terms of the mass spectrometer. The mass spectrometer needs very, very, very small amounts in order to get ratios, right?
So say you have like a 10 micron size sample.
Yes, you could theoretically do that. However, there is zero chance that you can tell me with 100% certainty that you have separated your phases at that scale.
Okay.
And that is the main problem with going to higher and higher pressure.
There's also procedural blanks on the column chemistry if you need to do that.
Right.
Okay. So I could make you a sample like that, where I would be totally sure that you could get that you would have a small portion that was just the iron, and the other portion would be just the silicate. But I was looking at your laser spots, and they're 80 microns. I mean, that's huge. I mean, my whole sample may not even be that big.
They're 80 microns because it's 8% silicon in that metal. It was an iron, right? In the silicate, they were much smaller because I have much more silicon. Laser ablation, you could not do this because you need a lot more sample for laser ablation, because it's somewhat unstable, right? It's for the solution you could do much smaller. And it would be great if I could get the two phases, but then on top of that, I need to know that they were at equilibrium at the conditions of the experiment. And those two things together, I think, are difficult because as you get to higher temperature, as you get to higher pressure, you need to go to very high temperatures in order to get the liquid-liquid. There's one paper where they looked at the iron isotope fractionation between perovskite and metal at 25 GPa. However, it was a solid experiment. And I think it's very difficult to prove isotopic equilibrium in a solid experiment.
I was going to ask you this later, but I just wanted to quickly get your comment actually on the nanosims and the potential then to be able to use that for diamond cell experiments.
So the nanosims is a great tool, and it can do isotope ratios, especially silicon, for example. Do you know what a SIMS is?
Start from the beginning.
Okay, a SIMS is it's a yeah.
Believe it or not, nanosims are much bigger.
A SIMS instrument is a secondary ion mass spectrometer. So basically, it's just a different way of ionizing and then basically getting the isotope ratios. But it's an in situ technique, right? You don't have to dissolve anything. It has lots of benefits in terms of spatial resolution. The nanosims has smaller spot sizes than the SIMS, and it is really, really wonderful if you're looking at very small things. So they use it a lot for cosmochemistry, for example. So at DTM, we use the nanosims gets used a lot for pre-solar grains, right? Things that are really, really tiny. And so you could imagine a diamond cell experiment is really, really tiny, and you could use the nanosims to kind of plot out what you have. And people have done this. The problem is that the error bars are way, way bigger. And when you're looking at fractionations that are pretty small, the error bars are too big.
just say it'd be the size of the square.
Yes.
So remembering what you said earlier in the talk, that things scale like 1 over temperature squared. If we go from 2,000 to 4,000 Kelvin, these fractionations will be 4 times smaller.
I will show you. Give me 1 second. So this is, these are the experiments that I showed you now as a function of 1 over t squared. And here is the big delta, so the little delta of silicate minus metal, right? And you see 1,800, 2,000, 2,200, 4,000, I don't know, here? Yes, very, very small. So Edwin, again, calculated, based on the experiments now, what the fractionation would be as a function of temperature and as a function of pressure, okay? We'll get into pressure in a little bit. These are the calculations he did for our 2009 paper, and then our 2009 paper just had 1 temperature, right? So our 2011 paper now we could get a curve as a function of temperature because we had more than 1 experiment. And what we found is that you could take the Georg et al. Data, right, the difference in the isotope fractionation between chondrite and bulk silicate earth, and you could take our experiments, and from that, you can pop out the percentage of silicon in the core. Does that make sense? At a particular temperature of equilibration, which is why this is a function of temperature. Okay, so if we pick a temperature, let's say 3,000 Kelvin. Now, I haven't put any error bars on these numbers. Okay, the error bar, this is the experiment. So based on the experiment, at the conditions of the experiment, we would say about 5 weight % silicon in the core, plus or minus 2. Okay, so that's pretty big. If we look at 3,000 Kelvin, we see that if you want a shallow magma ocean, shallow equilibration, you could put about 8 weight % silicon in the core. A bit deeper, you get about 9.5 or 10. But these numbers have error bars on them, so they're all about the same. The point is that you could get silicon in the core. You can calculate the amount of silicon in the core based on these experiments and the difference between chondrite and earth.
I have a quick question. I think I'm missing something here. You told us a minute ago that putting silicon into the metal doesn't really exert a very large lever on the silicon isotopes of the silicate.
But if you're talking about a huge core with 8 weight % or whatever,
so
it will change it from the the original bulk value. The experiments are really, really tiny, right? So.
I'm just curious what the silicon content of the iron metal in experiments were.
8.
8.
There's just a solubility at those conditions, right? And it's about 8 weight %. So does that make sense? We have an independent measure of the silicon content in the core just based on these experiments and the fact that we could measure the difference between chondrite and earth.
Has the original measurement held up?
Okay.
It's one of the things about new isotope methods is the first paper is always wrong.
Yes, that's right. So this brings up a huge can of worms, and I'm being taped. So I will tell you that the original paper has not held up. The difference between the chondrites and earth, there is still a difference. However, the difference is smaller than it was originally measured. There is, however, still a difference, and this gets into, oh no, okay, hold on. And this gets into whether or not people are doing the chemistry right. So the mass spectrometry was always right. The problem was that silicon chemistry is actually very difficult because you can't use HF because the silicon will evaporate. And so doing that chemistry and making sure that you have it right on a chondrite turns out to be very difficult. And so there is still a difference. It's just smaller than it was originally measured.
What is your comment on the Mars chondritic value of silicon isotope?
That it's
not fractionated with respect to chondrites.
It is not fractionated with respect to chondrites. Therefore, so Mars silicon isotope composition is equal, or for Martian meteorites, is equal to chondrite. Therefore, I would say there's no silicon in the core of Mars. Does that make sense? Okay.
This is based on
Yes.
one meteorite or something?
Well, no, we have a lot. We have like 50. How many Martian meteorites do we have?
From the crust?
From the crust. Their sugar tights are thought to be basaltic. I would say there's no silicon Martian core. But again, if we go back to FO2, right? Mars has more FeO in its mantle than Earth does. It formed probably, or is at higher oxidation state than Earth. No?
Well, the person was right to say.
Okay.
It possibly formed.
Right. It may not still be. That's right. Thank you. That's right. So it formed at higher oxidation state than the Earth. If you remember the silicon versus sulfur, at higher oxidation state, we're more likely to get sulfur into the metal, not silicon. So we will look for, if I can get, we'll look for sulfur in the Martian core.
One really quick question and one maybe more complicated. So quick question is, as the silicon isotope fraction, the difference between Earth and Condrites is it's gotten smaller and smaller. Have the error bars also gotten smaller on those measurements?
Yes, there's pretty good agreement these days
Okay.
as to what the Earth composition is in terms of silicon. There was a 2007 to 2010. There were sessions at AGU and at Goldschmidt that were dedicated to the silicon isotope composition of the Earth versus Condrite, and it has basically now been settled. We know what this value is, and yes, the error bars have gotten smaller, but also because there's so many more measurements.
Okay.
Right.
So that was, and then the next thing is, as we're, as let's say the Earth gets larger, and so the amount of silicon we can put in the core, so as we get to a higher temperature, the fractionation is smaller, and so with a given, so we could either put more or less, as you're showing, more or less silicon in the Earth as you're showing here, and so
That's right.
And so that number kind of not just depends on where you're actually in the Earth, you're segregating out the iron from the silicon, but also how, it depends where you are, but also how large the Earth is at the time.
Yes, so
right?
remember, the value that we are, the fractionation factor that I'm telling you, that I'm quoting here, is based on the pressure and temperature at which the silicate and the metal equilibrated.
Yeah.
Right? And then what happens after that, we're assuming nothing. Right? It goes, 3,000 kilometers downwards and nothing, it doesn't re-equilibrate. So the moon has the same isotopic composition as the Earth, which tells you about the timing of the giant impact. Okay? Yes?
So there is no variation in the silicon isotopes of Condrites?
Hold on. Take a deep breath. We're going to get there. Okay. So we have an independent measure of the silicon content in the core based on stable isotopes. We can do the same game for mercury. I don't have the citation here, but this is that science paper where they talked about the interior of Mercury based on messenger data. I will put the citation on there. But we don't have any meteorites from Mercury, right? But what do we know about Mercury? We know that Mercury has a huge core, okay? And we know that that core, that Mercury is extremely reduced. So reducing conditions put silicon into the core, right? The core is huge. So what can we do, just for fun? We can calculate what the silicon isotopic composition of a Mercurian meteorite would be. And then you can go to Tim McCoy at the Smithsonian and you can ask him for every meteorite he has in his collection. And if you get this value or something near it, you can find a Mercurian meteorite. Yes?
So apparently there really is a Mercury meteorite.
No, it's not really believed.
No?
No. There's no
The Peabody has one on site for the last 6 months, a piece of it.
It's not.
I don't know how they showed that.
Yeah, I wouldn't. I'm being taped.
Doesn't.
Yeah.
Doesn't this depend in somewhat? You're assuming that Mercury's core completely re-equilibrated with its mantle at its current core mantle fraction.
Yeah, I'm assuming
so
a lot of things.
in a sort of your first formation mechanism, you have complete disruption. This is probably a very good response. But if you have Mercury as being a survivor of either one or multiple impacts that are stripping events, you may not necessarily re-equilibrate your core and mantle.
I'm assuming that the core and mantle of Mercury equilibrated, and then nothing happened to it again. And that we could then measure a piece of the mantle, which would be the meteorite, and that it would be very positive. Whether or not this value, I mean, there are huge error bars on this value, right? I've assumed all sorts of things, the composition of the silicon, how much silicon is in the core, right? But the idea is that it would be positive, because there would be so much silicon in the core because it's so big.
But I would
It's so
argue that's
reducing.
not necessarily. I mean, it would be, if you found that, that would be really cool, because that would tell you something huge about the formation mechanism. But you could form Mercury in a way very similar to Mars and then just lose its mantle. And it could keep its same
That's
silicon
right.
isotope.
That's true. That's a good point. That's right. Oh, this is good. I like this.
Is it also possible to explain the isotopic difference between Earth and Condrite by vaporization?
There are people that have tried evaporation, vaporization. The problem is that magnesium doesn't show this same difference, and magnesium and silicon have basically the same volatility.
Goldschmidt in June, Tim Elliott gave a talk talking about the magnesium isotope difference between chondrites and the Earth. I'm sure it's still a number in flux, and the difference is very small.
Yes. You remember I asked the question afterwards. I said, how does this affect the silicon isotopes, right? Because that's right. So he's actually not the first one to show this. So there are 3 papers. Alex Halliday showed this at one point. Ed Young showed this, and now Tim Elliott has shown this, that there is a small difference in magnesium. I have a plot as like an extra slide where I can show you the difference between Earth and chondrite that people have measured for all sorts of different elements. And there is a huge, there are a lot of elements that are now this is being done for, right? Where you're measuring the Earth versus chondrite, and then if you find a difference, you try to explain where that difference comes from. So what Mark is saying is that at Goldschmidt this year, Tim Elliott gave a plenary, and he found that there was, I think it was a 9 ppm, is that right? A 9 ppm difference in magnesium between Earth and chondrite, and he was trying to explain why that is. So this is a very interesting field. Yes?
The Earth here is the mantle, or the whole Earth?
This is the bulk silicate Earth.
And does the crust look different from the mantle?
No. That's a good question. Paul Savage has done a lot of work looking at silicon isotopes in all sorts of Earth rocks, and they're all the same, within error.
Sorry.
Some OIVs.
He needs a microphone.
Some hotspots are actually about 0.1 per mil lower in delta
spots.
30S, shifted towards chondrite. So
Matt's saying that there are some OIBs. Yes, Matt said that there are some OIBs that push the Earth value towards chondrite by about 0.1 per mil. I didn't know that.
Sorry, going back to the vaporization question, does anyone calculate how much material you would need to vaporize and then lose in order to explain the Earth-chondrite difference?
I don't know. I don't think so. I don't know. People have done that for iron, but I don't think people have done that for silicon.
What is it for iron?
It's not very much.
Backing up for a second.
Since you're very dependent on the theoretical calculations of partition coefficients at extreme temperature conditions, you're in a temperature regime there that's very, very high. You're fairly high up on that potential curve you started your talk with.
Anharmonicity.
What? Yeah, I know. I was going to allude to anharmonicity, but also you have not just anharmonicity, but you have excitation of multiphonon effects. You have lots of things going on at those high temperature conditions. How really confident are you in the very high temperature theoretical inversions?
I'm confident. Okay, I'll tell you 2 things. One is I'm confident that 1 over T squared works, and that as you get to infinite temperature, you get closer to 0, and that we've been able to see that.
Okay, I agree with the second statement. I'm not sure I agree with the first statement.
Right.
Go ahead.
However, as an experimentalist, I want to test this. And so we're actually doing synchrotron experiments at low temperature, which I will hopefully get to later, to try to get away from anharmonicity and see if the low temperature versus the room temperature gives us the same value. and then maybe even higher temperature, so we can look for the effect of anharmonicity.
Yeah, but anharmonicity at 4,000 K is way different from anharmonicity at 300 K or even 1,000 K.
Valid. That's right. This is all assuming a harmonic. That's right.
It's a liquid.
Assumes harmonic.
So Bill is dying to ask you a question,
Potential curves
but he's too shy.
I don't think shy is the word I would describe.
No. Ask her. Go ahead. Continue.
I'm gonna get to Fitoussi and Bourdon. Is that what you want to get to?
Yeah.
I'm getting there. Okay. Okay. So the mercury thing was just more of like, oh look, fun. Okay. Boom. Okay. Bill's question. So in 2012, Fitoussi and Bourdon published a paper where in Science, where they looked at enstatite chondrites. Now remember this idea, where does the Earth come from? Can it be made from enstatite chondrites? Okay, and the reason, again, that I think at least that it started that maybe the Earth was built from enstatite chondrites is because of the oxygen isotope similarity between the Earth, Moon, and enstatite chondrites. They have the same oxygen isotope composition in big delta. You can talk.
The one thing I want to perhaps add, and maybe you'll do it, is the petrology of the different chondrites.
I was not. Go ahead.
Okay. So there are many different types, but there's basically 3 different types of chondrites: carbonaceous, ordinary, and enstatite. Now, the planet Earth doesn't look anything like a carbonaceous chondrite in terms of what we would call the phase proportion, because carbonaceous chondrite, the C1 type, has all the iron as iron oxide. It would never form a metallic core. The ordinary chondrites are a little bit more reduced, and so about half of their iron is in the metallic state, and the other half is an oxide. The enstatite chondrites are virtually all reduced, and in fact, if you think of olivine in enstatite chondrite, it really is FO100. It's actually FO99. So all of the iron really in that system is in the metal state. So to understand these coming data, you have to understand that the system has iron that could either be all oxygen or associated with all metal. Okay, and just to put in respect, the Earth, about 95% of the Earth's budget for iron is in the core.
Okay, so these data are both their data and a compilation of the previous data. So this also gets back to Paul's question as to how things have changed, right? So I don't know if you can read all of these, but basically it shows like, this study or these different studies. This is the original Georg et al. Paper. Raz Armitage has done a lot of this work as well. Karen Ziegler has looked at other mineral separates. The point is that the enstatite chondrites, okay, are not like other. So this, this is Earth. This is terrestrial. You notice there's a difference, okay? The Chakrabarty data we'll ignore for now, okay? Because they're very different than everybody else's. So we're just going to assume that this is chondrite, and here you have bulk enstatite chondrites. And what they've done it's relative to help. Silicon is relative to BHVO. Is that right?
That's what I thought it was.
Oh, okay. This gets back to the whole standard thing, right? But the idea is that for our purposes, this is chondrite, so this is the starting point, right? But enstatite chondrites aren't like this is the Earth, okay? The enstatite chondrites are lighter, so regular chondrites are like here, let's say. Enstatite chondrites are lighter. That's the point. Enstatite chondrites are lighter than other chondrites, making them even more different than the Earth. Okay, so we say for oxygen isotopes, the Earth is equal to enstatite chondrites. For silicon isotope, the Earth is not equal to enstatite chondrites. And they have used this, and the title of their paper is something along the lines of Silicon Isotope Evidence for a Non-Enstatite Chondrite Earth. Okay, So they've now used this idea that the silicon isotopes in N-type chondrites cannot equal the Earth and silicon isotope value, and therefore the Earth cannot be made from N-type chondrites. This is the plot that shows that. Now again, they've used our fractionation factor in order to make this plot, right? So they have their measurements, they use our fractionation factor, and they find that in order to make the Earth from N-type chondrites, you would need to form the Earth or differentiate the Earth at 1500 Kelvin, which is below the liquidus for peridotite, right? So you have no liquid silicate. So you can't differentiate the Earth at 1500 Kelvin. And in order to make their data fit a 3000 Kelvin differentiation, for example, you would need to put 28 weight% silicon into the core, which is not plausible, okay, both from mineral physics data and seismology and whatever. Therefore, you can't make the Earth from N-type chondrites. However, if you pick a random mixture, and they say that this is just an example that they just threw together, of other chondrites, you can form the Earth from a mixture of other chondrites at approximately the right temperature based on this difference between the bulk silicate Earth, silicon isotope composition, and bulk Earth. Does that make sense? Comments? No?
That's probably non-unique.
It's a non-unique solution. Their point was that you just can't do it from N-type chondrites. So this idea that you can build the Earth from N-type chondrites has been around for a while, and they're basically saying the silicon isotopes tell you that that's not true.
That I've heard some answers that are focused on condensation effect of SiO and SiO2 in the nebula that could actually be evidences for anisotropy chondrites based on the silicon isotope composition of the Earth. But it's not clear to me. I'm just saying there's some people arguing back against that in terms of supporting anisotropy chondrites.
Right. So this is kind of like what Paul said before, right? That when you get a new system, you get a new set of data that you hadn't seen before. There are all sorts of things you can play games with, right? The details come out in later years as to whether or not that's right or wrong, right? But the basic idea is that we have this huge new toolbox, and people are using that and making really big statements about the formation of the planet, right? From these silicon isotopes that are vibrating at different zero-point energies, right?
So when you mostly just talking about silicon stable isotopes, are there any other non-traditional stable isotopes that we can use to try and look at similar processes?
Why, yes, you can. Okay, really fast. Before I get to that, I don't have much time. So I'll just say that Emily Pringle, who works with Fred Moynier, has also taken that same isotope fractionation factor from the experiments, and she's looked at this a different way. She said, okay, I can measure the value from the silicon isotope ratios in HED meteorites, which are thought to come from Vesta, a differentiated asteroid, maybe. And she can say, based on the fractionation factor we found in the lab and the isotope difference between HEDs and other chondrites, they can say that not only the amount of silicon that might be in the core of Vesta, but also the FO2 conditions in which they think Vesta formed. Okay? Again, there are a lot of assumptions here, but you can see the games that people are starting to play. As to whether or not there are other systems, iron is an obvious one, right? So we have an iron light element core, and we have a silicate mantle. Well, the iron is another non-traditional stable isotope that has 3 easily measured stable isotopes, 1 not so much, but 3 easily measured stable isotopes that you can then play the same sorts of games with, right? And this is some of the newer work that we're doing. And the idea is that it's the same idea where you have the iron metal and the silicate. But in this case, we're not looking, we also looked at the regular fractionation just between pure iron metal and silicate. But we're also adding light elements into the metal and asking the question, does the composition of the core actually affect the isotope fractionation of the iron? So again, once you put sulfur into the iron, you don't have a sulfide, you have an iron-sulfur alloy. But the bonding environment for that iron will change, and therefore the isotope fractionation should change between the metal and the silicate. So we did these experiments where we looked at the effect of sulfur. And we did this in particular to look at Mars, because again, Mars is thought to have approximately 14 weight % sulfur in its core. Okay, so Philippe last week was talking about InSight, the new mission that's going to Mars, okay, the seismometer that's being put on Mars. Well, one of the things that we're hoping it will tell us is the structure of Mars, right? How big the core is, if it's liquid like we think it is there an inner core or what? And if there's a liquid core, then we can say, well, there's probably sulfur in it, okay? Because sulfur is like antifreeze in metal. It makes it really lowers the melting temperature significantly. And meteorites have told us that there's a lot of sulfur in the Martian core based on the Martian meteorites, okay? So we look again at the iron isotope fractionation between metal and silicate, this time as a function of the weight % sulfur in the iron-sulfur alloy, okay? And the green squares, just focus on those, show you that at 0 weight % sulfur, so just the plain iron isotope fractionation between metal and silicate, there is an iron isotope fractionation of about 0.1 per mil, okay? And as you increase the sulfur in the metal, you get more and more fractionation, okay? So this was very 1650. 1650 C.
Any other confounding variables that are different amongst those experiments?
So I took all those plots out because I didn't think I'd have time. We looked at, so this is an iron-nickel sulfur alloy. So we looked at the effect of the nickel. We looked at the effect of FO2, right? Because as you add more sulfur, you might be changing the FO2. We looked at the effect of the capsule material. We used a boron nitride capsule in order to have a very reducing environment. So we looked at the effect of the boron in the silicate, the nitrogen in the silicate, and there's no correlation with any of those. This is the only correlation we could find, okay? So, as I said, we like to play games with these new fractionation factors and data, and so I was very interested in the amount of sulfur in the Martian core, because this is Mars, okay, because Martian meteorites are chondritic in their iron isotope fractionation, or ratio, okay? So Mars equals chondrite, which on this plot is 0. So I took the fractionation factor from the experiments, and these different curves are different temperatures. Kevin Reiter and Nancy Chabot have done a lot of work looking at the siderophile element. Based on the siderophile elements in the Martian meteorites, they've been able to back out a temperature of core formation. So these are their temperatures with the error bars. And if I back calculate what a Martian meteorite the iron isotope composition of a Martian meteorite should be based on the sulfur in the core, I get a problem, right? So at the first Goldschmidt where I presented this, I said there's no sulfur in the Martian core because I wanted to kind of see what the reaction would be, right? And I'm not saying that there's no sulfur in the Martian core. I'm saying that there's probably less because these curves do not intersect this plot, right? Or this 0 line. So in order for there to be sulfur in the core, and assuming, huge assumption, that Mars formed from one magma ocean, they equilibrated, and then basically nothing happened after that, right? Then the Martian meteorites should actually be light in their iron isotope composition, but they're not. They're chondritic.
Which ones are high temperature? Which ones are low temperature?
This is like 2100 Kelvin plus or minus 200 Kelvin.
Which direction does the temperature push?
Oh, sorry. Temperature pushes you to less fractionation. So this is a higher temperature.
Okay.
I think this is 2300 Kelvin, this green one.
So it seems to be the problem with saying this is an argument for no or low sulfur is that with no or low sulfur, you still are light. I mean, if we go to 0 and you're still not intersecting, right?
That's right. This is an extreme view, right? I haven't put I haven't put error bars on things. But yes, that's right. So the idea would be there's no sulfur, right? But the truth is that there are a lot of assumptions being made in this temperature. There are assumptions, there are errors here, there are errors here. And what we say in the paper is that you could basically get up to 8 to 10 weight % sulfur in the core, assuming all of these assumptions, but probably not 14, which is what is determined from Martian meteorites.
I think what Mark is saying is that the mismatch is as bad at 0% sulfur as it is at 5% sulfur, so you can't really distinguish between modest amounts of sulfur and zero sulfur from that plot.
That's right. That's right. But I'm saying there are lots of errors that I know that go into that. That's right. Okay. So now we've covered. Oh, in case anybody hadn't seen how we know meteorites are from Mars, this is how we know meteorites are from Mars. They have the same gas in them as we can measure with satellites. I don't know if you guys have all seen it. Okay. So in the last 5 minutes, I have left out pressure. Okay, so all of you should be thinking, well, what about pressure? Does pressure have an effect on isotope fractionation? I showed you that one calculation that Edwin did, but the only pressure, the only reason that the high pressure line was separated from the low pressure line is because silicon perovskite has a different coordination than silicon in olivine, for example. Okay, so that wasn't necessarily pressure, it was just a phase change. But what about pressure, right? So the beta factor is the little, it's basically the reduced partition function. It's basically we'll just look at it as the isotope fractionation for now, okay? So the beta factor is proportional to pressure, and it's all due to this, what's called this delta volume, which is the molar volume isotope effect, is what people would call it in isotope speak, okay? So when we substitute a heavy isotope, we lower the vibrational frequency, we're shortening the bond, and therefore we're changing the volume. And pressure will have an effect on that volume. So is there an isotope effect associated with that change? Okay? And in 1975, Bob Clayton at the University of Chicago looked for it. Okay? And he looked, this is an oxygen isotope. This is calcite and water, or aragonite and water, depending on the pressure. And he went up to 20 kilobars, and he said, is there an oxygen isotope fractionation between calcite and water up to 2 GPa, 20 kilobars? And the answer was no. Okay? And I'm not kidding. Because of this plot, these data, the term pressure is negligible in isotope fractionation was then repeated over and over and over again in all the literature in stable isotope geochemistry. And they're right. It is negligible at 20 kilobars. Okay? What about higher pressure? So here is, well, I'm going to skip this for now because I don't have much time. So Harita, in 1999, published this paper in Science, or Nature, I don't remember, where they looked at the fractionation between D to H. Okay, so if you're going to look for an isotope fractionation, you go to hydrogen because it's the easiest one, it's going to have the biggest effect. Okay, and they looked at the effect, I think this is brucite and water, as a function of pressure. They only went to 800 megapascals, but they see an effect. Now, this is a fractionation between, this is amazing. Okay, this is the first pressure-dependent isotope effect that was measured in the lab that I know of. Okay, however, it's water, right? And water changes its density very, very quickly at low pressure. As you increase the pressure on water, it's really changing a lot. Okay, what if you're looking mineral to mineral, where the effects are way, way smaller than they would be between mineral and water? So for this, we go to the synchrotron. Okay, so this is my other instrument of choice, my, I guess, third order instrument of choice. This is APS at Chicago. And there's a technique called nuclear resonant inelastic X-ray scattering, which many of you in the audience are probably way more familiar than I am. But this technique probes the vibrational frequencies of the phase that you're looking at. So you have the X-ray, And it goes, and Nicolas Dauphas has been doing a lot of work on this. This is from his paper, but I just put a little diamond cell here because he doesn't work at high pressure and I do. So we go to the synchrotron and we put our sample in the diamond cell and we look and we can measure the average force constant of the iron. This only works for certain isotopes, just like Mossbauer, right? I can probe the average force constant of the iron in that phase that I'm looking at. And then I can do that as a function of pressure. And the force constant, as I showed you in the equations early on, is directly applicable, or you can just calculate the isotope fractionation. Okay? And we have done this, and this is for FeO. Okay? So you're looking at the force constant, and here's the 1,000 natural log beta. This is basically just the isotope fractionation factor of FeO as a function of pressure. This is 5, 20, 25, and 40 GPa. And what you see is that there's an increase. Okay? The two different colors are two different ways of calculating the beta factor from the data. There's a little bit of a disagreement as to how to do this, so we did it both ways to see if there was a difference. And the important point is that there's a pressure effect on FeO, okay, on the force constant as you get to higher and higher pressure. There's a difference in the beta factor, there's a difference in the reduced partition function, difference in the fractionation factor. There's this, it's not a straight line, and the reason we think it's not a straight line is because there's a phase change from cubic to rhombohedral at about 15 GPa, give or take, hydrostaticity in your diamond anvil cell. But so we think that that's actually, we can actually see that in the data because it should be a straight line. But point is that you can now start to do this and look at how different phases will change their beta factors as a function of pressure. And then if you have the pressure from the synchrotron, you have the temperature from the experiments we can do in the lab, and hopefully one day maybe even laser heated diamond cells, right? The thermal gradients are too large at this point. And you have the compositional effect that I showed you with the sulfur, and you can put them all together and you can start to model what the different isotope fractionation or ratios would be for all these different differentiation and formation of different planets, right? So Caitlin Murphy, as part of her PhD at Caltech, looked at this beta factor for iron, and she went to very high pressure. And she shows that there's this very nice pressure dependence for iron for the beta factor. So we took her iron, our FeO, and then the last time we were at the synchrotron, we also measured Fe3C. And the question is there a difference, right, between the Fe, the FeO? You look puzzled.
Well, everybody just shows beta and stops. You need two betas to get an alpha.
Yes, which is why I plotted it like this, right? So the difference between these lines is the alpha. So beta minus beta is alpha, is the fractionation factor, right? There's no fractionation when you're only looking at one phase. The isotopes can't go to a different phase, right? There's only one phase in the diamond cell. So what we did is we took Caitlin's iron, we took our FeO, and then we just also measured Fe3C, and we see that the alpha between Fe3C and Fe is greater than the alpha between FeO and Fe at high pressure. Okay? So now we're starting to look at pressure effects on the isotopes. And perfectly timed, this is my last slide. The point is that if you take experiments and meteorite data and then also mission data, right, so moment of inertia, things like that, or even if you can put a seismometer on Mars, you can start to come up with, you can play lots of games with trying to understand what's going on in planetary interiors with this tool of stable isotopes, which for so long was thought to be negligible for all these processes. Okay, thank you.
So fractionations get bigger as pressure goes up. Is there a simple explanation why? Because at higher pressure, things should look more similar.
The force constants, as far as I understand it, the force constants will compress and become stiffer, and therefore you'll have more of an isotope effect. Because as you compress them, thermal motions get smaller, right? And you get stiffer bonds, and you get more of an isotope effect. That's the way I've... Yes?
Now, in the Earth, we have mantle sitting next to core. Is that material then being reset and more homogenized because of the higher temperatures, say 4,000 or something like that?
If there is an interaction between the core and mantle such that they are...
Well, they're in contact, right? But it's
Right, but on the time scales of billions of years, if solid-state diffusion were important, on the time scale of billions of years, you would re-equilibrate whatever down there. And so people are now doing models where they're actually looking at the isotope composition as a function of depth, right? There's a paper coming out for silicon where they've tried to do this.
So you've shown this nice picture of a palisite a couple of times, and we have the disco island ions as well. Can we see effects in these ions?
I just got a NASA proposal to look at that. I don't know yet.
Okay.
I will be looking at this. So the idea of the NASA proposal and what you're getting at is that this picture on the left is a palisite, which I just find absolutely gorgeous. And the idea is that one of the ideas for how these things formed is that they were formed at a core mantle boundary of an asteroid, right? And so my hypothesis is that if we measure the iron isotopes in the olivine crystals and we measure the iron isotopes in the metal and we compare that to experiments we do in the lab, we can get a temperature of formation for the palladites. So palladites and other asteroids are very low pressure, so we don't need to worry about pressure. But we could probably get a formation temperature for the palladites.
Ooh. Silicon in the core. This question really is not directed at you, but perhaps at some of the experimentalists who've run such experiments. One thing I remember from previous experiments that were trying to put silicon into metallic phase found that in a sort of a silicate metal partitioning, titanium was being partitioned more strongly than silicon into the metal phase. If that was the case, we would see a significant depletion in the Earth's budget of titanium if the outer core has silicon as one of the dominant light elements. I don't see that in the data. Does that negate this process? And this might be answered by some of the experimentalists.
I don't have an answer for that. I work on major elements. Right. Silicon, magnesium, I have no idea.
Titanium's major.
I have no idea.